Hi guys, and welcome to another video. Today we're going to be looking at the fundamental counting principle, and specifically we're looking at an example dealing with codes. This is from the November 2011 paper 3, and it reads as follows. The digits 0, 1, 2, 3, 4, 5 and 6 are used to make 3-digit codes. How many unique codes are possible if digits can be repeated? So there are two ways in which we can solve this particular question. Now firstly, let's look at how many items do we have to be arranged. We've got 1, 2, 3, 4, 5, 6, 7. So therefore n is equals to 7. So the number of items to be arranged is 7. And how many places do we have to arrange them in? They are 3-digit codes. So therefore r is going to equals to 3. Now, the formula that we can use would be as follows. So for 5.1, the number of items to be arranged is 7, and the number of codes that we have or places that we have to arrange them in is 3. So therefore we can use the following formula. N to the power r equals to 7 to the 3, and 7 cubed. 7 to the power 3 is 343. So that'll be 343. Alternatively, we can do this. It says how many unique codes are possible if digits can be repeated. The keyword there is repeated. So all we do is got 1, 2, 3 positions. The number of items that we have to arrange is 7. So therefore in position 1 we have 7, in position 2 we also have 7, and position 3 we have 7. Therefore 7 times 7 times 7 will also give us 343 unique codes. 5.2. How many unique codes are possible if digits cannot be repeated? So if digits cannot be repeated, we can use the formula, which is n factorial all over n minus r factorial, where n is the number of items that we have to arrange and r is the number of places that we have to arrange them in. So once again, we know that we have 7 digits, so 7 items to arrange, so that will be 7 factorial all over 7 minus 3 factorial, and that's now equal to, so that will be 7 factorial all over 7 minus 3 factorial, and that's equal to 210. 210. So just a quick word on factorial notation. What is factorial notation? Now remember that factorial notation is the product of positive integers less than or equal to n. A very quick example. What is 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1, which will equals to 120. Remember that we can only have the factorial of a natural number. Alright, so let's look at 5.3. In the case where digits may be repeated, how many codes are numbers that are greater than 300 and exactly divisible by 5? So for 5.3, we're going to draw our 3 positions, 1, 2, 3. So now they say that digits may be repeated. How many codes are numbers that are greater than 300 and exactly divisible by 5? Now for numbers greater than 300, the number has to start with the following numbers. So it has to start with either a 3, 4, 5 or a 6. So 3, 4, 5 or 6. So therefore for position 1 you can have 3, 4, 5 or a 6. So therefore you can have 1, 2, 3, 4 possible digits. They tell us very clearly that digits may be repeated. So therefore you have all 7 digits to choose from in the second position. Lastly, they tell us that numbers are greater than 300 and exactly divisible by 5. So for divisibility by 5, if we go back to our numbers, we can clearly see that we have a 0 and a 5. So therefore, numbers which end with a 0 and a 5 are divisible by 5. So that's 0 and 5. So we got 2 digits to choose from there. But this question, they tell us that the number must be greater than 300. So if the number must be greater than 300, there is a case where we could have 300. So there is a case where you can have 300. Therefore, we have to subtract 1. So it'll be 4 times 7 times 2 and minus 1 for the case where we can have 300, which is 300. Because the question clearly says that the number must be greater than 300. So let's put that in our calculator. And that will be 4 times 7 times 2. And we'll subtract 1, which will give us 55 unique codes. So our answer there will be 55. Learners, if you haven't subscribed already, please do subscribe to JL Maths and check all the videos on jlmaths.com. And I'll catch you in the next video.